with vector valued functions. We're going to figure out how we can represent a particular graph with a vector valued function. So we want to translate from the graph to a vector valued function. And then we're going to talk about continuity and differentiability of vector valued functions. And then we'll have all the tools that we need to actually do the real work that we're going to do. That's when things start getting fun. I mean, even more fun, right? All right. So what we want to do today is be able to translate from a graph, like I said, to a vector valued function. So we're just going to start with some examples. We want to find a vector valued function for the boundaries of this region. And we're just going to do a two-dimensional graph to make our lives a little easier at first. So here's our region. We're at the origin here, and we're going over here. This should be x, to x equals 10. And then we're going to, the other side of our region is here. And we have a curve here. And our angle here is 45 degrees. And this portion is x squared plus y squared equals 100. So we want a vector valued function for this boundary. We have three different parts here. So we need to break this up into three different. We'll break it up into three different functions. So I'm going to call this first one that's along the x-axis. That's going to be region 1 or boundary 1. This will be boundary 2, and this will be boundary 3. So for boundary 1, how could we represent that as a vector valued function? Anybody have an idea? R of t equals when we want to travel from here to here. So we want a function that lets us travel along here as our parameter changes. So you're on the right track. Ti. And our limits on t, 0 less than or equal to t less than or equal to 10. So as t varies from 0 to 10, we travel along boundary 1. Boundary 2. We need to parameterize this curve. We need to come up with, represent this in terms of one parameter. How do we, anybody have an idea of how we want to do that? So Anne says cosine t squared plus sine t squared. So we want some kind of trig function, right? And we want to start, depending on how we do our parameter, we want to start here where x equals 10 and y equals 0. So let's say that x equals And we need a 10 here to get our 100 over here. 10 sine t.
How would you use sine instead of cosine?
I am going to go for, I'm going to let t vary from, on this boundary, I don't have to have the t's, the same domain for the t's. So I'm thinking I'm going to let t vary from 0 to something on this second boundary. So if I start at t equals 0, this will get me at x equals 10. So I'll be at this point.
T equals 0.
When they
It's
cosine the x equals
Let's see, cosine of, yes, you're right. I got it backwards. Thank you. Cosine of t, thank you. So x equals cosine t. Y equals sine 10 sine t. So x squared plus y squared equals 100. And how is t going to vary here? So r of t equals 10 cosine t I plus 10 sine tj. So Scott says if we're in degrees, t can just go from 0 to 45. So we could say 0 less than or equal to t less than or equal to 45 degrees. And we could pick a different name for our parameter here. We could call t theta. If we were in radians, we could say t goes from 0 to pi over 4. And let's see, when t, let's figure out what this point is up here, so that that'll help us with our third boundary. When t is 45 degrees, x equals what? 5 square root 2. And y equals 5 square root of 2. All right, so there's our second boundary. We have a vector valued function for our second boundary. Now we need boundary number 3. If we're at an angle of 45 degrees, how could we represent this as a function of x and y? Jan says y equals x. So this is just a piece of the line y equals x. So we have y equals x. And we're going from the point 5 square root of 2 down to 0. So how do I need to write my vector valued function?
Negative.
Could be negative. We could say y equals, and we could do it a lot of different ways. Remember, parameterizations are not unique. If we wanted t to vary from 0 to some number, we wanted to start at t equals 0 on our third boundary also. How could we set that up? Anybody have an idea? 5 square root of 2 minus t, and x equals 5 square root of 2 minus t, because y equals x on that boundary. And as t varies from 0 to 5 square root of 2, y would go from 5 square root of 2 down to 0, and x would go from 5 square root of 2 down to 0. Oops. So vector valued function for boundary 3 is 5 square root of 2 minus t I plus 5 square root of 2 minus tj for 0 less than or equal to t less than or equal to 5 square root of 2. So we'll see problems like this kind of problem will crop up. You'll see them in the homework where we need to parameterize some region in the xy plane. Just break it into pieces and look at each one separately. And remember, the parameterization is not unique. We could have done some kind of negative. Start with a negative t in the x and the y to get us to go from our point down to 0. Put some kind of negative in there, like Anne suggested. So there's a lot of different ways that we could do this. Any questions on that? Yeah.
Why did you start from the top point and go down to 0? Why couldn't you start at 0, comma?
Oh, okay. I forgot on my graph that we wanted to go, our orientation was this way. So that's why it shows the parameters to vary the way they did. That's a good question.
Will it show?
Yes, it'll. The problem will give you the orientation that you're looking for.
Okay.
Because remember, when we represent curves with parametric equations, that introduces an orientation. So we have to be careful about our orientation. Thanks for catching that in. So any questions? All right, now we're going to do one that's a little trickier. I really like this one. We want to sketch the curve and find a vector valued function for the intersection of these two surfaces. And I remembered my k today. So we have the intersection of x squared plus y squared equals 4, and z equals x squared. And we want to represent the curve with a vector valued function. And our parameter is going to be x equals 2 sine t. So the first thing we want to do is sketch what the intersection of these two surfaces is going to look like, and then we want to represent that intersection with a vector valued function. So let's figure out what these surfaces are. So the first one is circular, but remember we're talking we're in 3 dimensions. Circle in the xy plane, and what can z be? If we're just talking about this surface, z can be any value. So if we have x squared, if we have a circle, there we go. It's a cylinder. It's circular in the xy plane, and it's the same for any z value. So this is a cylinder. And the axis is the z-axis. How about z equals x squared? So we have a parabola in the xz plane, and what can y be? Any value. So what kind of surface does that give us? So, so Danny's kind of making a little, like a trough shape, right? And Emily's making trough motions with her hands. So this is we call this one a cylinder also. So this is a parabolic cylinder. So this is a parabolic cylinder. So let's sketch these. Let's sketch these surfaces and figure out what their intersection is going to look like. And then we need to come up with a vector valued function. So our cylinder, I'll do the cylinder in. I'll do everything in black because we'll do the intersection. So we have a circle, and our cylinder is going to look like so. And we're going to have a parabola in parabola is parallel to the YZ plane. I'm sorry, the XZ plane. So my parabolic cylinder is going to, I'm going to draw it out from the other cylinder a little bit here.
But they're really in the same spot,
right? Right, and we're going to take this and go this way with it because y can have any value. And we want to figure out, the way I think about these when we're looking at these intersections is if this cylinder were made out of clay and the parabola was a really like a wire that you're cutting through that piece of clay with, what shape is it going to cut out of that cylinder? So as this parabola travels along the y-axis, the first place it's going to hit is right here, and as it travels through this cylinder, it's going to cut out. If we project the shape onto the XZ plane, we're going to get a parabola. It's going to cut out a shape that kind of looks like this, and then back behind here, it goes up to here, and then down like this. So as it goes through this cylinder, kind of like a saddle, so it's going to cut that little saddle shape out of the cylinder. And I made a sketch this morning, or a graph, that looks a little better than my drawing. So let's take a look at that. So there's our intersection. So I graphed this graph's parametric equation. So x is 2 sine t, y is 2 cosine t, and z is 4 sine squared t. And I kind of gave away our vector valued function. But so our y-axis is right along the middle here. And we see we get a parabolic shape here. That's where the parabola intersects the sphere. This is along the x-axis at these high points, and then we're back down here on the y-axis again. So this is what if we looked at it straight along the y-axis, we would see our parabola, and that's where it would cut through that cylinder. The cylinder would be, sides of the cylinder would be along here. Everybody see that? Okay. Now we want to represent this as a vector valued function, and we're using the parameter x equals 2 sine t. So if x equals 2 sine t, and we need a circle in the xy plane, what is y going to be? Scott says 2 cosine t, just like we've been doing in the past to represent a circle. So x equals 2 sine t, that's the parameter that we were given. So y equals 2 cosine t. And we get x squared plus y squared equals 4 from this. And z, what is z going to be? Z is x squared. So z is going to be 4 sine squared t, using this parameterization. So our vector valued function is r of t equals 2 sine ti plus 2 cosine tj plus 4 sine squared t k. And that's what I plotted in that parametric plotter. I put this for x, this for y, this for z. And have I shown you that? Did I show you that that MBT before? Did I show you that last semester? The website that I used.
That does the 3D.
This will do 3D plotting. It'll do parametric plots. It's from the University of Colorado Applied Math. If I just Googled CUMVT, Mathematical Visualization Toolkit is what it stands for, and it'll do it'll graph surfaces, it'll graph polar graphs. It's a really nice, easy tool to use to visualize some of this three-dimensional stuff that we'll be doing. And
Can we spin it so that we can see the circle?
the circle. So that's straight down the, it's not quite circular, I don't have it quite perfect. That's pretty close. So that's straight down the z-axis. So we see the circular shape on the xy plane. It's kind of fun. All right, any questions on that? And this MVT, if you're having trouble visualizing the surface, trying to figure out what something looks like, is a really nice way to get some more information if you're working on a problem. It is free. It's just you just go to the website. You can download it to your computer, but you can also just run it as a Java app just online. And I just went online and went to their website and did that this morning before class. All right. So we're good on that? Last thing for today, we're going to talk about limits and continuity.
Is it still in the same chapter?
Yes. We're just going to extend the ideas of limits and continuity from what we know about functions of two variables to vector valued functions. It's a pretty straightforward extension. So if we have a vector valued function, if we have r of t, and we have our component functions f of ti plus g of tj plus h of tk. We say that the limit as t approaches some number of our vector valued function of r of t is just the limit of the, we take the limit of each component function. It's the limit as t approaches a of f of t I plus the limit as t approaches a of g of tj plus finally the limit as t approaches a of h of tk. So we just take the limit component by component. And this works as long as the limits of each of f, g, and t exist. I'm sorry, not FGT, FGH exist. And most of the theorems that we've worked with before with limits apply to the limit of vector valued functions. We just go component by component. So just like we worked with vectors before, where we looked at we separated it into three different. We just looked at three components separately. We do the same thing with limits. We just look at the limits of each of the components. And excuse me. And the similar idea holds for the continuity of vector valued functions. We say that R of t is continuous at t equals a if, do we remember our definition of continuity from two variable functions? We'll talk about epsilons and deltas a little later, but just our definition of, not the definition of a limit, just the definition of continuity. If our function is continuous at a point if okay, so Scotty says that our limit coming from the left, the limit coming from the right, and the limit at the point, everything has to be, they all have to be the same. So what we say, just in a little more formal language, our limit exists and the limit as t approaches a of r of t equals r of a. So the limit has to exist, and the limit at the point, at our point, has to be the function value at that point. So that's our definition of continuity. And it's saying exactly the same thing that Scotty said. We have to be able to find the limit, and the limit has to be the function value at the point that we're interested in. That tells us that our function is continuous. And this is exactly the same ideas as we have for functions of two variables. We just apply it component by component. Questions? Yes.
Are you going to juggle?
Am I going to? I forgot. You know what? I forgot so much this morning. I spent last night, I got some toilet paper tubes, and I made a little model of the intersection of those two surfaces. I cut the one so it was a parabola, and I cut the other one, and I put them together, and I set it on my desk, and it's still sitting there. And then when I got to going up the hill on Davison Mesa, I was like, I didn't bring anything to juggle, and I didn't bring my toilet paper tube model. So I apologize.
I think I have those tape holes.
You still you still have those?
I have one.
All right. Homework.
Whoa.
There you go.